Okay, all right. Let's begin then. June 2020, paper 4, variant 1. We're going to be doing difficult questions from this paper. Let's have a look at this. I'll go through the questions myself alongside as well, in case there's any that I find difficult that maybe we can discuss. Okay, so the first one, we just have to find the magnitude of the resultant and state its direction. That's straightforward. Okay, so car and a trailer. They're connected by this. Power is this. Okay, that's Newton's second law of motion and power formula. Greatest height above the ground reached by P. Okay, we've done similar questions to this before. Multiple questions like this. Greatest value of T for which the ring remains at rest. You just use the limiting equilibrium case here. Acceleration of ring with tension is PA. RF equals NA. Okay, so let's have a look at these questions then. Questions 5, 6, and 7 from this paper. That's what most of you have voted for. Okay, all right. So let's look at these questions then. Question number 5, question number 6, and question number 7 from this paper. These are 3 questions in particular that you guys are asking about. Please do it for the other papers as well. If you for the other paper as well, if you haven't already. For paper 4, variant 3, paper 4, variant 3 as well. Okay. Okay, let's start with this. Question number 5 from this paper. It says a child of mass 35 kilograms is swinging on a rope. So mass of the child is given. The child is modeled as the particle P and the rope is modeled as a light and extensible string of length 4 meters. Initially, P is held at an angle of 45 degrees. So that this is the initial position. Given that there is no resistance force, find the speed of P when it has traveled halfway along the circular arc from its initial position to its lowest point. Okay. So they basically want that when the child who is modeled as this particle, when he has reached halfway along the circular arc, what does that mean? So this is the circular arc. The angle here is 45 degrees. Halfway means here. What do we know about this point? If that complete angle was 45 degrees, we can say this angle would be half of that. What's half of 45? It's 22.5 degrees. Okay. We need to find the speed of P at this particular point. And that's what we're looking for. We are given the length of this of that string, that is 4 meters, and that's it. Okay, now how do we think about this? It's an arc. Whenever you have a circular arc like this, remember, you cannot use constant acceleration formulas because the direction of the object is changing at every single point. Since the direction is changing, acceleration is changing. So constant acceleration formulas cannot be used here because acceleration is a vector quantity, right? So since the direction is changing, that means acceleration is changing, and those formulas are not applicable. Sometimes they give you correct results, even if you apply them, but you will have deduction of marks in that case as well. Even if the answer is correct, since you can't assume that the acceleration is constant, even if it gives you the correct result in some case, that will not be completely acceptable. You will get some partial marks for that, but not complete marks. So make sure whenever you have an arc like this, a surface that is not straight, when it's a curve, you cannot use constant acceleration formulas. Okay, so what do we do instead? In such problems, whenever you have a curve or an arc like this, you always use energy method. Okay, how do we use that here now? What's the energy method? This is one equation that we know about. Work done by driving force, that is equal to change in potential energy plus the change in kinetic energy plus work done against resistance. Now, in this case, since they're saying there's no resistance force, there is no resistance force, and there's no driving force as well. There's no one who's pushing the child, right? He's just released from rest, right? That's what it says. Let me see. Doesn't say anything like that. Yeah, so initially P is held at an angle of 45 degrees to the vertical, and then he is released from there. There's no driving force as well. When there's no driving force and there's no resistance, remember, you can also use conservation of energy, right? In this case, energy would also be conserved. At every single point in this diagram, energy would be conserved. Energy would basically be the same. So let's call this point something. Let's call this point A, where the particle started from, and let's call this point B. The total energy at A and the total energy at B, they're supposed to be equal to each other. So we can just equate the two. We can say kinetic energy plus the potential energy at the point A, they should equal the kinetic energy plus the potential energy at the point B, right? They're supposed to be equal to each other. Now, what is the kinetic energy at the point A? The object started from rest, that's 0. Potential energy at the point A. Now, what we can do for this is, we can consider this point as ground. Consider B as the ground, right? Because all that we're interested in is how much is the change in energy. So we can consider B as the ground level, right? So at B, we would suppose for this particular part that the potential energy is 0, okay? Now, how high is A as compared to the level of B? What's the difference in vertical height of A and B? We need to find that difference. What we can do for that is use this right angle triangle. We can say we have a right angle like this. And now in this right angle triangle, can we find anything? Let's think about this. We have the hypotenuse. We can find the length AB. That is something that we can find. If hypotenuse can be found, can we find an angle using that? If that angle is 22.5. That means that complete angle is 45. In fact, if that complete angle is 45, that means this angle would be 45. And if this is 45, we could actually find this angle here as well. Now, there might be actually a simpler way of figuring this out somehow. Let me see if I can figure that out. That angle is 22.5 and okay, let's do it this way. So this angle is 45, right? Why? Because these are alternate angles, the ones that I've encircled. These are alternate angles. Now, what about this angle? If the angle here is 22.5 degrees, it's a string. This line, this length would also be 4 meters. These both are 4 meters. Since they are both 4 meters, it's an isosceles triangle. This triangle, let's call this point O. The triangle OAB is an isosceles triangle. If that's an isosceles triangle, I can write down this angle as well. How would that be calculated? 180. That's the total angle, the sum of all angles in this triangle. 180 minus 22.5 divided by 2. Let's see what that gives me. 180 minus 22.5 divided by 2, that's giving me 78.75. This angle is 78.75. If this angle is 78.75, I can now find the remaining angle, this one as well as this one. I can find both angles here now. 180 minus 45 minus 78.75. This angle is 56.25. And this one would be 22.5. No, sorry. Let me calculate that again. 180 minus 22.5 divided by 2. That's 56.25. 90 minus 56.25. That's actually 33.75. This angle would be 33.75. Now, can I find the change in height using this now? If this angle is 33.75, what about this length? Length of AB. This angle is 33.75. Now, if this is 33.75, let's actually find this length AB. Let's see what this length is. Length of AB. We've got the angles and we can use sine rule for this. What's the length AB? AB over sine of 22.5 degrees. That equals 4 over sine of 78.75 degrees. Let's see what the length of AB turns out to be from this. 4 into sine of 22.5 divided by sine of 78.75. This is giving me 1.5607 for AB. And then using this, we could find the change in height here. What's that? Let's call this H. H would be H over AB. AB is 1.5607. That equals, let's say, sine of 33.75. I'm using this angle, 33.75, with respect to this angle. H is perpendicular and AB is hypotenuse. And that will give me the change in height into sine of 33.75. That's turning out to be 0.8671. That's the change in height that I'm getting. So this, from A to B, the change in vertical height is turning out to be 0.8671. If that is the case, what's the potential energy at A then? Mass of A, do we have that? 35. Mass of the particle at 35 into G, which is 10, into height. At A, the potential energy we're saying is 1.5607. And then kinetic energy plus potential energy at the point B. Potential energy at the point B will be considered 0 because we are considering that as ground level. Then half into mv squared, half into 35 into v squared plus this should equal this. And we'll see what this turns out to be. 350 into 1.5607 multiplied by 2 divided by 35 and then square root of that. 35 and 35, they will get cancelled on both sides, in fact. Try that again. Okay, I'm sorry about it. I input the wrong thing again. I'm sorry, I put the wrong thing here. So we were doing kinetic energy plus potential energy at the point A. Mass was 35, G was 10. And we had to input H here. And instead of H, I, by mistake, input this thing here, 1.5607. This should have been this H that we've calculated, that's 0.8671. That's the value that we should have input here. And this turns out to be, now let's do this again, 35 and 35, they get cancelled. 20 into 0.8671, and then square root of that. That's going to be 4.16. 4.164, yeah. This is 4.16. Okay, so this was all fine. I input the wrong value here. But still, I think this question statement is kind of confusing. It says, oh, okay. So that kind of makes sense as well now. If we read this whole thing, halfway along the circular arc, so I was reading this part of it when I read it again. So it says when it's traveled halfway along the circular arc from its initial position to its lowest point. So basically, from the initial position to its lowest point, the halfway point of that. So halfway between A and the lowest point, that's this point that we have here at an angle of 22.5 degrees. That's what we are looking for. And then when we calculate the height for that, you have to make sure that you input the correct height here. The height was actually 0.8671. All right, so I input 1.5607 there by mistake. It should actually have been 0.8671. All right, I'm sorry about that. So that's the velocity that we get. That's the speed at that point halfway along that circular arc. Let's look at the next part. It says it's given instead that there's now a resistance force. The work done against the resistance force as speed travels from its initial position to its lowest point is x joules. Okay, so now it is actually reaching the lowest point. Let me just copy this diagram here. Now it's going to its lowest point, starting from P. Okay, now this is the second part. It starts from this point. Let's call this point A again, where it starts. And from that point, it reaches this point. Let's call this point L, the lowest point. And now there is a resistance force. Now, if there's a resistance force, that means if there is a resistance force, that means we can't conservation of energy anymore. That is not going to work. All right, conservation of energy is not going to work. So what do you have to do instead? We have to use this formula: work done by driving force that equals change in kinetic energy plus the change in potential energy plus the work done against resistance. Okay, we can't use conservation of energy anymore because now we've got resistance. If we have resistance, energy is not conserved. Now, what's the work done by driving force? There's no work done by driving force still, but there is resistance. Okay. What about the change in kinetic energy? It says the speed at the lowest point is 4 meters per second. It started from rest. The speed at the lowest point is 4 meters per second. What's the change in kinetic energy? It's half into m was 35, into v squared, which is 4 squared minus 0 squared. That's the change in kinetic energy. And what about the change in potential energy? What would that be? Again, we need to do that calculation. What's the change in height here? Okay. Now, how do we do this calculation again? Let's think of this triangle. And now let's say this is H. And again, we don't have any of these this information, but now this is going to be 45 again. And if this angle is 45, it's an isosceles triangle with 4 meters here, 4 meters here. What's the angle that we get here? 180. Let me just write that down here. 180 minus 45 divided by 2. You get 67.5 here. So this angle is 67.5 and this angle is 67.5. This is the right angle. What about this remaining angle now? This is also 22.5. Let's use this one. Can you find the length AL somehow? Let's use sine rule for that. AL over sine of 45. That equals 4 over sine of 67.5. I'm using this triangle. In this case, I can find the length AL and see what that turns out to be. 4 sine of 45 divided by sine of 67.5, and that's giving me 3.0615. That's the length AL. Once you have length AL, you can use H over AL. AL is 3.0615. If we consider this angle, 22.5, H is perpendicular, AL is hypotenuse, so H over 3.0615, that will be sine of 22.5 degrees. And that will give you the value of H. And you can see what this turns out to be. Sine of, answer into sine of 22.5 degrees. And the change in height now turns out to be 1.1716 for me. That's the value of H. That's the change in height. So what's the change in potential energy now? M, which is 35, into G, that's 10, into change in height. Change in height here is negative. So we say it's minus 1.1716 plus work done against resistance. What's the work done against resistance? They've told us the work done against resistance is X joules. And we have to find the value of X. So we just have plus X here. And from that, we can find the value of X. And you can see what this turns out to be. Can somebody please do this for me as well? So I'm not making a careless error again. $35 over 2 multiplied by 16 minus 35 into 10 into 1.1716. And that goes to the other side, becomes plus, so that's 130.06 joules. Or you can say it's 130.1 joules. Or just leave it like that as well. That's fine. That's the value of X that we get. Okay, that's the second part. That's part B. Any problem with this? So basically the main problem was finding the angle and using that to find the change in height. Once you have the change in height, the rest is not that difficult. Okay, that was part B of this question. Let's move on to the next one. So from this paper, you asked about question number 5, 6, and 7. Let's have a look at 6 now. Now it says the particle moves in a straight line AB. The velocity v of the particle t seconds after leaving A is given by this. Where k is a constant, the displacement of the particle from A in the direction towards B is 2.85 when t equals 3 and is 2.4 meters when t equals 6. Find the value of k and hence find an expression in terms of t for the displacement of the particle from A. Okay, so how do we think of that? We've got the velocity function. So it's a straight line AB. We've got the velocity function. Let's write that velocity function. V equals k into t squared minus 10t plus 21. That's the velocity function. The displacement of the particle from A in the direction towards B. So if this is A and this is B, they're saying this is the positive direction from A to B, okay? This is 2.85 when t equals 3. So at time equals 3, they're saying the displacement is 2.85. And then 2.4 when t equals 6. When t equals 6, the particle comes back a bit. Displacement from A becomes less than it was before. This length is just 2.4 meters. And the time value here is time equals 6. Okay, now this is an important piece of information. Find the value of K first of all. Okay. The displacement is starting from point A as well, and the function is starting from that. How do you go from velocity to displacement? How do you go from velocity function to displacement function? You have to integrate, right? Now, there's no information given directly that you can use to find the value of K directly from here. You don't have any particular time value at which we know the velocity, right? You can read the whole question statement. There's no velocity value that we're given at any particular time. We are only given displacement values. So what we can do is we can say, let's integrate it first. Let's start by integrating this. When we integrate this, let's see what we get. K is a constant, multiplying by the whole thing. We can keep it outside as it is. Let's integrate this. Integration of t squared, that's t cube over 3, minus 10 t squared over 2, plus 21t. Now, we are looking for the displacement function. We want an expression for displacement. It's not that we are finding displacement from one point to another. In that case, we can use limits. Here, we're looking for an expression for displacement. Here, we need to have a plus c. So we will have a plus c like this. And now this is the displacement function. And the problem is we don't know what the value of c is. We don't know what the value of k is. For this, what we can do is we can use the information that's given in the question. It says the displacement of the particle from A in the direction towards B is 2.85 when t equals 3. That's one point that we're given. So what we can do is we can say, let's input t equals 3 and displacement equal to 2.85 here. And then also, we are given that when time equals 6, the displacement is 2.4. That's another point that you can input there. When you input both of these points there, you'll get two equations. One in terms of C and K. You can solve them simultaneously to find the values of C and K. Let's try this. In this integral, 2 and 10 will get cancelled to give you 5. And now let's input those values. In place of S, you input 2.85. On the right side, you've got K into t cube, that means 3 cubed divided by 3, minus 5 into 3 squared, plus 21 times t, plus c. Now you can simplify this whole thing, and that will give you 2.85 equal to 3 cubed, which is 27 over 3, minus 5 into 9, plus 21 times 3. And that's giving me 27. So that's 27k plus c. That's one equation. You get another equation from the other set of points. T equals 6 and displacement equal to 2.4. 2.4 equals k into 6 cubed divided by 3 minus 5 into 6 squared plus 21 into 6 plus c. You have another equation in terms of k and c from here. Let's simplify this and see what that gives us. 2.4 equals 6 cubed divided by 3 minus 5 into 36 plus 21 into 6. And that's giving me 18k plus c. You have these two equations. You can solve these simultaneously to find the values of k and c. Let's see what they turn out to be. In the first equation, if we make c the subject, that gives us 2.85 minus 27k. In the second equation, it becomes 2.4 minus 18k. We can equate both of them to find the value of k first of all. Let's see what this turns out to be. 2.85 minus 2.4 divided by 9. And that's giving me 1 over 20. That's the value of k. And now we can find the corresponding value for c as well. Let's put that here. C equals 2.85 minus 27 into 1 over 20. And the value of c is 3 over 2 or 2.5. Now, once we have the values of k and c, we can input them back in that original displacement function to find our final function. What does this turn out to be? S equals k, which was 1 over 20, multiplied by t cube over 3 minus 5t squared plus 21t plus c, which is 3 over 2. You can leave it like this, or do they ask you to simplify this? They don't. You can leave it like this as well. If you want to simplify this, it would become t cube over 60 minus 5 over 20. That's 1 over 4. That's 1 over 4 t squared plus 21 over 20 times t plus 3 over 2. That is what the displacement function becomes in terms of t. And that's your final result. Is that okay? That's what you're looking for in this part. So you just find the displacement function. By integrating, you have two unknowns, k and c. You have 2 points given. You use those 2 points to find the values of k and c. Okay, now it says find the displacement of the particle from A when its velocity is a minimum. So we've got a velocity function and the displacement function. The velocity function looks like this. It's okay. Now that we know the value of k is 1 over 20. So velocity function can be written as 1 over 20 into t squared minus 10t plus 21. We want the value of displacement when velocity is a minimum. Now we've got the displacement function. If we know the time value when velocity is minimum, we can just input that time value in that function, in the displacement function, to find the corresponding displacement. Now, how do you find that time value when velocity is a minimum? It's a quadratic function, right? It's a quadratic function. And it's a U-shaped function. We are looking for the time value of the starting point. You can do that by differentiation. You can do that by minus b over 2a, or whichever method you prefer. If we do differentiation here, you can find dv over dt. What would that be? 1 over 20 remains as it is. Derivative of t squared is 2t. 10t is 10. That's the derivative that you get. You put this equal to 0. 0 equals 1 over 20 into 2t minus 10. 20 will go to the other side, get multiplied by 0, and you get 0 from that. 2t equals 10 and t equals 5 from that. This is the value of t when v would be minimum. Okay, so we found the value of v when value of t when v is minimum. Now that we've got this value, we can input this value in the displacement function. This is the displacement function, right? And that will give us the displacement at that point. So you've got this displacement function. Put that value of t here. 5 cube over 60 minus 1 over 4 into 5 squared plus 21 over 20 into 5 plus 3 over 2. And you can see what that turns out to be. Okay, you can evaluate this and see what that is. 125 divided by 60 minus 25 over 4 plus 21 into 5 divided by 20 plus 1.5. That's 31 over 12, which is 2.58333. That's a displacement. That's a displacement that we were looking for. Okay, this was quite straightforward. Both parts, not that difficult. We found the point, the value of t when v was minimum, and then just put that value of t in the displacement function to find the corresponding value for displacement. Okay, that is question number 6. No problems in this? Can we move on? Okay, let's have a look at the next question now. Question number 7. It says a particle P of mass 0.3 kilograms lying on a smooth plane inclined at 30 degrees to the horizontal is released from rest. Okay, it's released from rest. It's on a smooth plane and its mass is 0.3 kilograms. Its initial velocity is 0 meters per second. It slides down the plane for a distance of 2.5 meters and then reaches the horizontal plane. There is no change in speed when P reaches the horizontal plane. Okay, so basically, when it shifts from the inclined surface to the horizontal surface, there's no immediate change in speed. Okay? There's no instantaneous change in speed. Whatever was the speed at the last point, at the bottom of the inclined plane, that's the same as the speed at the start of this horizontal plane. Okay, so speed does not instantaneously change. That's what they're saying. A particle Q of mass 0.2 kilograms that lies at rest. (1.5 meters from the end of the inclined plane on the horizontal plane. P collides directly with Q. Okay, so you've got this distance given in the diagram as well. It's given that the horizontal plane is smooth. Okay, so in the first part, it says it's given that the horizontal plane is smooth in the first part, and that after the collision, P continues moving in the same direction with speed 2 meters per second. Find the speed of Q after this collision. Okay, now there are two parts of this journey. You see, P is first moving down the plane like this, and then it starts moving on the horizontal plane. It collides with Q, and then something happens after collision. So their speeds change after collision. We need to find the speed of Q after this collision happens. Now, first of all, let's break this journey down into two parts, because there is some part of the journey that's happening on the inclined plane, and then the particle moves on the horizontal plane. Let's divide this into two parts. Let's call this point something. Let's say this point where the particle P is starting from. Let's say this point is A, and then the bottom point where the horizontal plane starts, let's say that's point B, and let's say this is point C, where the actual collision happens. So first of all, let's talk about A to B. For particle P, let's see what happens from A to B. What do we know about that? The inclined surface is a smooth surface. It's a smooth plane, right? The inclined plane is a smooth plane. And the only force acting on the particle P is its weight, right? It's released from rest here, and it's a smooth surface. If it's a smooth surface, that means there's no friction, no resistance. The only force acting is the weight of the object, okay? Now we know whenever there's a smooth inclined surface and weight is the only force acting on the object, acceleration of the object in that part is given by 10 sine theta. So we can write down the acceleration of the particle P directly. We can say that's 10 sine theta, where theta is the angle of inclination of the plane. That's 30 degrees. So it becomes 10 sine 30 degrees, which is 5 meters per second square. That's the acceleration of the particle. P is moving down the plane, so we're considering down the plane positive. So since gravity also acts down the plane, acceleration value is positive here. So that's acceleration. What else do we know about the journey from A to B? We know the displacement. S equals 2.5. We know the initial velocity. It's started from rest. So we have three pieces of information for the journey from A to B. What we can do is we can find the final velocity at the point B, right? Because then we need to understand what happens from B to C afterwards. For that, it would help if we know what speed B starts from here, okay? So what's the speed at B? Speed at B would be the final velocity for this A to B part of the journey. Which equation can we use to connect these four things? 2as equals v square minus u square. And that gives us 2 into 5 into displacement, which is 2.5, equals v squared minus 0 squared. And that will give us the velocity. 2 into 2.5 is 5, and then square root of that, we get 5 meters per second. This is the velocity of the particle when it reaches this point. Okay, this is 4.5 meters per second. The speed of the particle P at this point B, 4.5 meters per second. Sorry, why 4.5? 5 meters per second. I wrote 5 there. Yeah, 5 meters per second. Okay. And now the particle starts moving on the horizontal plane from B to C. What happens from B to C? The horizontal plane is also smooth. Now, if the horizontal plane is smooth, there is no force acting in the direction of motion from in B to C direction. There's no force acting here or here. So the resultant force is 0. If the resultant force is 0, that means acceleration is also 0, right? Resultant force equals mass into acceleration. Forward force minus backward force equals mass into acceleration. If this is 0, that means acceleration is also 0. So from B to C, there is no change in velocity. It's a smooth surface. Whatever the speed of the particle was at the point B, it remains the same. It does not change. Okay, so from B to C, the initial velocity was 5 meters per second. The final velocity is also 5 meters per second. Why? Because acceleration is 0. There's no acceleration. Okay. And that means when the collision happens at the point C, the velocity of the particle P was 5 meters per second. So now we can use momentum because now P and Q are colliding. So you can think of P and Q colliding now. We have P here and we have Q here. They're colliding with each other. What do we know about the collision? As in, what do we know about before collision and after collision? Before the collision, P is moving towards right, towards Q at a speed of 5 meters per second. And Q was at rest, right? Q lied at rest there, 0 meters per second. After collision, we know that P continues moving with speed 2 meters per second in the same direction. That means towards right. So P continues moving towards right at a speed of 2 meters per second. What about the velocity of Q after collision? Let's call that VQ. That is what we're looking for. Do we know the masses of P and Q? We know the mass of P is 0.3 kilograms. We know that the mass of Q is 0.2 kilograms. And now we can use conservation of momentum to find this missing velocity. How do we do that? We can say momentum before collision. That equals momentum after collision. What's the momentum before collision? Mass of P, which is 0.3 into velocity of P, which is 5. We are considering right side positive for both the particles. Keep that in mind. Momentum is a vector quantity, so you have to be careful about positive direction. So 0.3 into 5 plus 0, because the momentum of Q is going to be 0, its velocity is 0, equals momentum after collision, that's 0.3 into 2, plus 0.2 into VQ. And from that, you can find the velocity of Q just after collision. And see what that turns out to be. 0.3 into 5 minus 0.3 into 2 divided by 0.2. And that is giving me 4.5 meters per second. That's the speed speed of Q just after collision. All right. So we looked at what happens from A to B. The speed at the point B is 5 meters per second. That becomes the speed for the horizontal part of the journey. And we use that as the speed just before collision. And then use conservation of momentum to figure out what happens right after collision. Okay, that's the velocity of Q after collision. And that's what we were looking for. Let's look at part B now. It says it's given instead that the horizontal plane is rough. And that when P and Q collide, they coalesce. Coalesce means they merge to form one single object. They merge and move with speed 1.2 meters per second. Find the coefficient of friction between P and the horizontal plane. So now it's a rough surface. The horizontal plane is rough now. What about the vertical plane? Nothing has changed about the vertical plane. Inclined plane. The inclined plane is the same as before. It was a smooth plane earlier. It's still a smooth plane. So what we found about the inclined plane in the first part, that the velocity of B was 5 meters per second, that's still the same. Okay, velocity at B is still 5 meters per second. Let's mark this point here again. This is point B, let's say. This is point C. At point C, we had this particle Q. And at B, let's say we've got the particle P, which is moving towards right at 5 meters per second. At B, the velocity of the particle P is 5 meters per second. But now B to C part is rough. Do we know the distance of this part? 1.5 meters. B to C is 1.5 meters. That is what we're given. What we need to find is coefficient of friction. Where does coefficient of friction come? In which formula do you see coefficient of friction? It's F equals mu R, right? So basically we have to find the value of friction and reaction. When we have both of those things, we can find the value of mu. Now reaction, we already know. For P, the weight of the object is 3 Newton, right? There's no other vertical force acting on the horizontal plane. So if weight is 3 Newton, reaction is also going to be 3 Newton. So we know about reaction, that reaction is 3 Newton. So this R value is 3. The only problem is we don't know what the friction is. Once we can find friction, we can say F equals mu R, and we can find the value of mu from that. So the only problem is finding the value of friction somehow. Now, how do you find friction? Friction is a force, and we have information given about kinematics quantities. What connects kinematics and forces? Newton's second law of motion, right? Resultant force equals mass into acceleration. So we'd have to use that somehow. That's somewhere. Okay, now let's think about this. What's happening from the point B to C now in this second part? What information do we have? We have initial velocity, that is 5 meters per second. We've got displacement. Displacement is 1.5. And that's it. That's all the information that we have. Since we want to find friction, we want to somehow find acceleration, right? Because when we have acceleration, we can use resultant force equals mass into acceleration to find the missing force, which is friction. But the problem is, how do you find acceleration? What other things do you have here? Final velocity, do you know that? No. What's final velocity? Final velocity is basically the velocity just before collision with Q. Can we find that somehow? We've got information about collision given. They've given us that when P and Q collide, This is P and this is Q. We know about what happens at the point of collision. Before collision and after collision. Let's see what information we have about that. Before collision, we know nothing about P, but we know that Q was at rest. Q was at 0 meters per second. We don't know what the velocity of P was. Let's call this VP. After collision, the two particles coalesce and move with speed 1.2 meters per second. So before collision, it was two particles. There were two particles. After collision, it becomes a single particle. Let's call that PQ. That is moving at a speed of 1.2 meters per second to the right. Okay. Now, do we have the masses of both the particles? Mass of P is 0.3 kilograms. This is 0.3 kilograms. Mass of Q is 0.2 kilograms. What about the mass of PQ? The coalesced mass, that's 0.5 kilograms. We can use conservation of momentum. We can say momentum before collision, that equals momentum after collision. What does that give us? 0.3 into Vp plus 0.2 into 0, that equals 0.5 into 1.2. And using this information, what we can actually do is we can figure out the velocity of P just before collision. Let's see what this is. 0.5 into 1.2 divided by 0.3, and that's giving me 2 meters per second. This is velocity of P just before collision. So you use conservation of momentum to figure out what the velocity of P was just before that collision happened. Okay. And now we can say just before collision happens, we can say that's the final velocity of this part of the journey from B to C. So this would actually become 2 meters per second here. The final velocity of the particle P from the point B to C. And now using this information, what we can do is we can find the value of acceleration. 2as equals v squared minus u squared. What does that give you? 2 into a into 1.5. That equals v squared, which is 2 squared, minus u squared, which is 5 squared. And you will get a value for acceleration from this. Let's see what that is. 4 minus 25 divided by 3. Acceleration turns out to be negative 7 from this. So from B to C, we know that the value of acceleration is negative 7. Is that okay? Any problem with this? You got the value of acceleration? Okay. Once we've got the value of acceleration, now it's pretty straightforward. We can say, since this is the acceleration, resultant force equals mass into acceleration. What's the forward force? On P, there's no forward force, right? P is just moving to the right because it already has some speed. There's no forward force. What's the backward force? Backward force is friction. So on P, we have a backward force of friction acting. So we say 0 minus F. That equals mass of P, which is 0.3, into acceleration, which is minus 7. Friction turns out to be 2.1 Newton. Now, what is friction? Friction is mu into R. Mu R equals 2.1. The value of R, what's that? 3 Newton, because the weight is 3 Newton. Reaction is also going to be 3 Newton. So mu into 3 equals 2.1, and that gives us 2.1 over 3. And that turns out to be 0.7. That's the value of mu that we were looking for. Is that okay? That's what we get from this. Energy method, yeah, you could do that as well, but it's not going to make this much simpler. You would have to do this part anyway. You have to apply conservation of momentum to figure out what the speed just before collision would be. And then instead of this part, you could use energy method, and that would work as well. Yeah, you could do it instead of this part. All right, so that's the value of mu that we were looking for. That's the second part of this question, and that's it. That's all that we had to do from this paper. No problems in this? No questions? Okay, let's have a look at the next paper now. So the next paper that you had to do was June 2020 paper 4 variant 3. Let's quickly have a look at that. And do difficult questions from that paper as well now. So there are 3 questions that I have some words on. Let's do those 3 questions. June 20 paper 4 variant 3. Okay, let's start with this one now. June 2020 paper 4 variant 3. So you're asking about questions 5, 6, and 7 from this paper as well. Okay. The first question is a simple momentum problem. Okay, and then okay, diffusion power forces switching the last one. Yeah. Okay, let's start with this one. Question number 5, 6, and 7. Let's have a look at these 3 questions quickly. Okay, let's start with this one. Question number 5 from this paper. June 2020 paper 4 variant 3. A block B of mass 4 kg is pushed up a line of greatest slope of a smooth plane inclined at 30 degrees to the horizontal by a force applied to B. Okay, now let's draw this diagram to understand the situation better. You've got the mass 4 kilograms, and this block is being pushed up a smooth plane that's inclined at 30 degrees to the horizontal. This angle is 30 degrees. This block is being pushed up the plane. Its weight is 40 Newton. Acting in the direction of motion of B, so there's a force acting in this direction. That's what they're saying. The block passes through points P and Q with speeds 12 meters per second and 8 meters per second. So there's this point P, let's say, and there's this point Q, and we are given the speeds at those 2 points. P and Q are 10 meters apart, but P below the level of Q. Okay, so this distance from P to Q, that is 10 meters. And we are given their distances. Find the decrease in kinetic energy of the block as it moves from P to Q. Decrease in kinetic energy? Let's find the change in kinetic energy. How do you do that? Half into m, which is 4, into v squared, which is 12 squared, minus, sorry, the other way around, 8 squared minus 12 squared. And that's going to give you the change in kinetic energy. Let's see what this turns out to be. 64 minus 0.44 multiplied by 2. That's minus 160 joules. That's the change. They asked for the decrease. You can say the decrease in kinetic energy, that is equal to 160 joules. That is what we were looking for. Okay, that's the decrease in kinetic energy. Now it says, hence find the work done by the force pushing the block up the slope as the block moves from P to Q. Now that should remind you of something. They've asked you to calculate change in kinetic energy or decrease in kinetic energy. And then they're asking you for the work done by the force. Which equation connects these things? The work energy principle, work done by driving force, that equals change in kinetic energy plus the change in potential energy plus work done against resistance. Now, it's a smooth plane. So there's no friction. That means there's no resistance. Work done against resistance is 0. Remember, weight is not considered as resistance. So work done against resistance is 0. Work done by driving force, that's what we want to find out. Right? This force that's applying, what's the work done by that? That's what you want to find out. That equals change in kinetic energy. Change in kinetic energy is minus 160. Right? Remember, the change is negative here because the energy was decreasing. What about the change in potential energy? Because once we have that, we can find the work done by the driving force or the pushing force here. Now, for that, we need to find the change in height. How can we do that? We can use a right angle triangle for that. If this is P, this is Q, you can say this distance is 10 meters. This is H, the change in height. This angle is 30 degrees. How do you find H? H over 10 equals sine of 30. And that will give you the value for H, which is going to be 5 meters here. So change in height is 5. So M, which is 4, multiplied by 10 into height, change in height, that's 5, plus 0. That should give you the work done by the driving force or the work done by the pushing force. You can see what that turns out to be. 40 into 5 is 200, 200 minus 160, that's 40 joules. That's the work done by the pushing force that we were looking for. Okay? Using the work energy principle. Let's move on to the next part now. Now it says, at the instant the block reaches Q, the force pushing the block up the slope is removed. Find the time taken after this instant for the block to return to P. Okay, now what's happening is, let me actually draw that diagram here again, slightly bigger. Let's say this was the inclined surface, this is 30 degrees. Let's say this point is P, and this point is Q. The distance between P and Q is 10 meters. What they're saying is, at the point Q, the force pushing the block up the slope is removed. So there's no force acting in the forward direction anymore. And is it still a smooth surface? Yeah, it's a smooth surface. How much time does it take for the block to return to this point P? Now, what do we know about the distance from Q to P? About the journey from Q to P? We know that this distance is 10 meters. Now, what happens from Q to P? Do we know the initial velocity of the particle at the point Q? Of the block at the point Q? It says it was 8 meters per second, and it was moving up the plane, right? At the point Q, the speed is 8 meters per second. In which direction is Q moving? It's moving up the plane. It's moving in this direction, right? So we consider this direction is positive, in which it's moving initially. We say this direction is positive, right? Up the plane, we're considering positive. Keep that in mind. That's very important here. Otherwise, we'll get confused between negative and positive directions, between negative and positive values. So you need to be very clear which direction you're taking as positive. This direction is being taken as positive. If up the plane is positive, what's the initial velocity? Initial velocity is 8 meters per second. What else do we know? Do we know displacement? What is going to be displacement from Q to P? Anyone? What's the displacement from Q to P? What value do we use for that? Remember, we're taking up the slope positive. QP is down the slope. So displacement value is going to be negative. Initial velocity is 10. We would say displacement is negative 10 here because it's down the plane. And then, since weight is the only force acting now, there's no other force acting on this particle because the forward force is removed and it's a smooth surface. What about acceleration? It's a smooth surface, weight is the only force, acceleration value is going to be 10 sine theta. That's 10 sine 30. However, since you're taking upwards positive, this acceleration is going to apply down the plane because it's because of weight of the object. We would say this is negative 10 sine theta, and that turns out to be minus 5. So we've got u, we've got s, we've got acceleration. We can find the value of t from this. Which equation connects these four things? S, u, a, and t. S equals ut plus half at square. We can use that. And see what the time taken turns out to be from this. S equals minus 10. U is 8 into t plus half into minus 5 into t squared. You can solve this equation to find the value of t from this. Minus 10 equals 8t minus 5 over 2. Let's actually multiply the whole equation by 2 to get rid of the fraction. That will give us minus 20 equals 16t minus 5t squared. 5t squared minus 16t minus 20 equals 0. Can you factorize this? This cannot be factorized, right? So let's input values in the quadratic formula. Minus into minus 16 plus minus square root of minus 16 whole squared minus 4 into 5 into minus 20 whole divided by 2 into 5. What do we get from this? Now you can write down the answers directly after this. You can see what this turns out to be. Okay, so I'm getting t equals plus 4.16 and t equals minus 0.961. Now, time, of course, cannot be negative. So we ignore this possibility. So this is not possible. So the time taken for this journey is 4.16 seconds from that point Q to the point P. Is that okay? No problems? That was part C of this question. Let's move on to the next one. Okay, question number 6. It says a particle travels in a straight line PQ. The velocity of the particle t seconds after leaving P is v meters per second, where v equals this. Find the velocity of the particle at the instant when its acceleration is 0. Now, how do you go from velocity to acceleration? You have to differentiate this thing, right? In order to go from velocity to acceleration, it's differentiated. Derivative of 4.5 is 0. 4t becomes 4, and then you have 0.5 into 2, that's 1 into t. This is the acceleration function. You put acceleration equal to 0. What value of t do you get from that? 0 equals 4 minus t, t equals 4. You put this value of t back in the velocity function to get the corresponding velocity. Velocity equals 4.5 plus 4t. 4 into 4 minus 0.5 into 4 squared. And you will get your result from this. You can see what that turns out to be. 4.5 minus 16, sorry, 4.5 plus 16 minus 0.5 into 16. And that's giving me 12.5. This is the velocity of the particle when the acceleration is equal to 0. And that's what we were looking for. That's the first part, pretty straightforward. Now it says, the particle comes to instantaneous rest at Q. Find the distance PQ. Okay, now how do we do that? We've got the velocity function. Velocity function is 4.5 plus 4t minus 0.5 t squared. That's the velocity function. Now the particle comes to instantaneous rest at the point Q. How do we find that point, first of all? when it comes to instantaneous rest, we put v equal to 0. Rest means velocity equals 0. And we get this equation from this. 0 equals 4.5 plus 4t minus 0.5 t squared. It's a quadratic equation. We can solve this quadratic equation to find the value of t when velocity equals 0. Let's multiply the whole equation by 2 to simplify this a bit. It becomes 9 plus 8t minus t squared. And that becomes t squared minus 8t minus 9 equals 0. Can we factorize this now? Yes, we can say this is t squared minus 9t plus t minus 9 equals 0, t minus 9 and t plus 1. Which means t either equals 9 or equals minus 1. This is not possible. It cannot be negative, right? So the only value of t that we've got is t equals 9. This is what is going to give you the point Q. All right, this is point Q when the particle comes to instantaneous rest. We need to find the distance PQ. What's P? P is where the particle starts. So that's at time 0. So now we can just use limits with integration because we've got velocity function. How do you go to displacement function from velocity? You integrate it. And now since you want to find displacement from one point to another, you can just integrate and input the limits. Let's see what we get when we do that. What's the integration of this? S equals 4.5t plus 4t squared over 2 minus 0.5t cubed divided by 3. All you have to do is input limits from 0 to 9 here, right? Initial point was 0. Point P was when time was 0. Point Q is when time equals 9. Just input these limits and you would get the result. Displacement equals 4.5 into 9 plus 4 and 2 get cancelled to give us 2 here. 2 into 9 squared minus 0.5 into 2 cubed divided by 3. Subtract from this the case when you have t equal to 0. In that case, everything is going to become 0 here. 0 plus 0 minus 0. And you will get the displacement from P to Q. Let's see what this turns out to be. 4.5 into 9 plus 2 into 81 minus 0.5 into 8 divided by 3. So 0.5 into 9 plus 2 into 81 minus 0.5 into 8 divided by 3. And that's giving me 201. Can somebody check this calculation as well? That was 2. Am I putting everything correct here? 4.5 into 9. Minus 0.5 into 8. Can somebody check this? What this turns out to be? This number? When you input 0, everything does become 0, right? Yeah. We have 4.5 into 9 plus 2 into 81 minus 0.5 into 8 divided by 3. Rizal, can you do this as well? I placed 2 in limits. Oh, I'm sorry. Thank you. I'm glad I'm not giving these papers again because I'm doing so many careless errors. Okay, I'm sorry about that. This was supposed to be 9 here. So that becomes 81. So this displacement is 81. All right, and that's what we were looking for. This turns out to be 81. Okay, that was part B. And that's it. That was quite straightforward. This whole question number 6. And that's 9 marks. Both parts were fairly straightforward. Generally, this is a question that you will find relatively easier question on kinematics, the one in which you have equations. These ones are more difficult, where you have to use constant acceleration formulas, because this sometimes comes along with momentum. Sometimes it comes with Newton's law of motion. In this case, it's also coming with energy, and that becomes more complicated. These equation questions are mostly relatively straightforward. And in this case as well, it was not that difficult. Okay, let's have a look at this one last question now. Question number 7 from this paper. It says 2 particles A and B of masses 3m kilograms and 2m kilograms respectively. They are attached to the ends of a light and extensible string. The string passes over a fixed smooth pulley which is attached to the edge of a plane. Again, let's highlight the important information. This is 3m, this is 2m. The plane is inclined at an angle theta. A lies on the plane and B hangs vertically 0.8 meters above the floor, which is horizontal. Initially, A and B are at rest. Given that the plane is smooth, find the value of theta for which A remains at rest. Okay. The value of theta for which A remains at rest. If A remains at rest, that means we are looking for the value where the opposite forces here remain equal to each other. Right? What are the forces acting on B? At B, we've got weight of B. What's that? If 2m is mass, weight is going to be 2m into 10. That's 20m. And there's tension acting upwards. What are the forces acting on A? We've got weight of A. That's 30 times m. We've got reaction. Although in this case, we would not really need to use that because the plane is smooth. So reaction is not going to be used. We only use that generally when there's friction. But then you have components of, so there's also tension, by the way. You have components of weight. If this angle is theta, this is also theta. This component of weight is going to be 30m into cos of theta. And the other one is going to be 30m sine of theta. Now we just equate opposite forces. T equals 20m. And from here, T equals 30m sine theta. So T equals both of those things. We can get an equation directly. We can say 30m sine theta should equal 20m. Right? If we consider the whole system, we can say this value should equal this value. All right. You can do that individually as well. You will say T equals 30m sine theta. And then from here, T equals 20m. You just equate both of them and you get this result. Okay. Now m and m get cancelled and sine theta equals 2 over 3. 20 over 30, that's 2 over 3. You can see what the value of theta here turns out to be. Sine inverse of 2 over 3. Let's figure this out. That's 41.81 degrees. 41.8 degrees, that's the first part. Okay, so we just resolved the forces, equated the opposite forces. Now it says it's given instead that the plane is rough. Theta equals 30 degrees and the acceleration of A up the plane is 0.1 meters per second square. Show that the coefficient of friction between A and the plane is under root 3 over 10. We need to find the coefficient of friction. And now we're given that the plane is rough. Angle is 30 degrees. So theta is 30 degrees. And acceleration is also given. That's 0.1 meters per second square. Now that the plane is rough, acceleration of A up the plane. So A is moving up the plane. They've given that information here. If A is moving up the plane, what about friction? Friction is going to act down the plane. It's going to oppose the motion. That's where friction acts. And now we need to find the coefficient of friction. What do we do in this case? Let's consider both the particles one by one. We've got particle A and the particle B. Now for A, forces acting perpendicular to the surface, they are always equal. R equals 30 m cos theta. These two are going to be equal, right? R and 30 m cos theta. R equals 30 m cos theta. And in fact, angle is 30 now. Let's put that here, cos 30. What does that give us? 30 into cos 30. Let's do that on the calculator directly. 30 cos 30, that's giving me 15 under root 3. 15 under root 3 times m, that's the value of R. Okay? Perpendicular to the surface, these forces are always equal to each other. Now, what happens along the surface? What's the forward force? A is moving up the plane. The forward force is tension. Backward forces are friction and 30 m sine theta. So we say, in this case, we apply Newton's second law of motion. Resultant force equals mass into acceleration. Because along the surface, there's movement. P minus friction minus 30 m sine theta. Right? These are the forces acting opposite to motion. That equals mass, which is m, into acceleration, which is 0.1. Okay. And now we can say P minus F, since the object is moving now, friction is at its maximum value, mu into R, minus 30 m into sine 30. Let's actually input that here. Sine of 30 degrees. Sine 30 is 1 over 2, so that becomes 15 times m equals 0.1 times m. Now, T minus mu into R value is this. We can say T minus mu into 15 under root 3 times m minus 15m. Or let's actually take it to the other side. 15m goes to the other side. It becomes 15 plus 0.1. That's 15.1 times m. That is one equation that we're getting in terms of T and M. T, mu, and M. Okay. Let's talk about V now. V is moving down the plane, right? V is moving down the plane. For B, the forward force is 20 m. Let's use resultant force equals mass into acceleration on that as well. Forward force is 20 m, backward force is tension. Right? B is moving down the plane, 20 m is the forward force. B is moving downwards, not down the plane, it's moving downwards. 20 m is forward, T is backwards. That equals mass of B, which is 2m. Okay, I'm sorry about that. Mass was not m. For A, the mass was 3m. And for B, the mass is 2m. Let me correct that here. On the right side here, it should have been 3 times m. So it's 3m into this. It becomes 0.3m and 15.3m. For B, the mass is 2m. Okay, so it becomes 2m into acceleration. Okay, I'm just checking if I have used 3m anywhere else on the left side. 30m, this is fine. It was coming from the earlier side. Now we know the value of acceleration as well. What's acceleration? Acceleration is 0.1. Let's input that here as well. And that gives us 20m. Or let's make T the subject. 20 minus 0.2. And that's 19.8.
19.8 times m. That's the value of tension that we get from the equation for B. Now put that in the first equation. What does that give you? 19.8 m minus 15 under root 3 m times mu. That equals 15.3 times m. Now m is appearing in every single term. All terms have m. We can take that common, remove that, and that leaves us with 19.8 minus 15 under root 3 times mu equal to 15.3. Now we need to make mu the subject. It's going to be 19.8 minus 15.3 divided by 15 under root 3. Put that on your calculator. Hopefully it should give you something like this. Try that. 19.8 minus 15.3. That's 9 over 2. So you can write it like this if you want first. 9 over 2 over 15 under root 3 divided by 15 under root 3. And that simplifies to under root 3 over 10. And that's what you have to prove. 1 over 10 under root 3. Put that on your calculator. Your calculator will do this work for you. You get this from that. 1 over 10 into under root 3. This is what we had to prove there. All right, that's the value of mu that we were looking for. We have proved that. That's part B. Make sense? Now let's look at the next one. It says when B reaches the floor, it comes to rest. Okay, now what's happening is B is going downwards, and at some point it hits the floor. And when it hits the floor, it comes to rest. Find the length of time after B reaches the floor for which A is moving up the plane. You may assume that A does not reach the plane. Okay, now again, it's that type of problem where the string becomes slack at some point. There's a lot of clutter on this diagram already. You will do this using a pencil, as in annotating on the diagram. That will be done with a pencil, so that for the next part you can erase that. I can just copy this like this.
Okay, so this is what the diagram looks like. It says when B reaches the floor, it comes to rest. Okay, now B is moving downward and A is moving up the plane. At some point, B hits the ground. A would have traveled the same distance in this direction. How much is that distance? 0.8 meters. The distance that B is above the floor initially. Okay. Let's call this point something. Remember, in such problems, we break the journey into multiple parts. We say, let's say this point is X, let's say this point is Y. And now at Y, A would have some speed, right? It would not be zero at this point, it would be some positive speed. Let's say that's 2 meters per second. Let's assume, I'll change that, but it will be some speed, right? It's not going to come to instantaneous rest here. It will move on for a while, and then gradually its speed is going to become zero. All right. So now we can say after Y, it moves on for a while until its speed becomes zero at this point. Let's call this point Z. Now remember, we were given this at the start of part B. It's given instead that the plane is rough. It's before part B. That means this condition also applies to the third part. Okay, part C also has a rough plane. Okay. Now, what does that mean? Let's break this journey down to two parts, from X to Y and Y to Z. Now from X to Y, let's see what information you've got. A is moving up the plane. What do we know about the particle from X to Y? Its initial velocity, it started at the point X, it started from rest, did it? Yeah, so it started from rest. From X to Y, initial velocity is 0. We're talking about particle A, right? Initial velocity is 0. What else? We know acceleration. From the previous part, we found the acceleration while the string was taut. So remember, from X to Y, the string is taut. At Y, B hits the ground, and when B hits the ground, the string no longer remains straight, so it's no longer taut. From Y to Z, we would say that the string is slack. We're talking about X to Y part for now. From X to Y part, do we know acceleration? Have you found that in the previous part? In fact, they've given this acceleration. They're saying acceleration is 0.1. So for this part of the journey, we also know acceleration, that's 0.1. Do we know displacement? Yes, we also know displacement. Displacement from X to Y is 0.8. And now what we can do is, remember what we do in such problems, Y is the common point between these two parts of the journey. So at Y, we can find the velocity because that will serve as the initial velocity for the next part of the journey. Let's find final velocity for this. V, A, S, and U, which equation connects these four things? 2as equals v squared minus u squared. What do we get from that? 2 into 0.1 equals v squared minus 0 squared. We will get a value of v from this. That's square root of 0.2. That's the velocity of the particle at the point y. Now that becomes initial velocity for y to z part of the journey. So here, initial velocity is under root 0.2. Now, what about the final velocity? When it reaches its maximum point, its velocity is going to be 0. So we also know the final velocity. What we need to find is the time taken after B hits the floor. So basically time taken from Y to Z. T is what we have to find out. Do we have any other information? We don't know what the distance from Y to Z is. We don't know what the... Okay, I'm sorry about that. Yeah, thank you. This is 2 into 0.1 into 0.8. There was 0.8 there as well, which I missed. That becomes 0.2 into 0.8, which is 0.16, 0.16, and the square root of that gives me 0.4. This velocity is actually turning out to be 0.4, not 0.2. Let me check that again. 2 into 0.1 into 0.8, and then square root of that, that's 0.4. Okay. Initial velocity is actually 0.4, not under root 0.02 as I wrote earlier. Okay, so now we have initial velocity and the final velocity. We don't have time. That's what you have to find out. We don't have displacement. We don't have acceleration. Can we find any of those things? Displacement is not given. Can we find acceleration somehow? We can find acceleration using forces now from Y to Z. Let's think about the forces acting on the particle in this part of the journey from Y to Z. Let's say the particle was here. What forces are acting? There's no forward force because there was tension earlier, but now there's no tension. There's only weight component that's acting against motion. We calculated that earlier. That was 30m into sine theta and friction. These two forces are still acting. 30m sine theta and friction. I'm actually represented on the side here. From Y to Z, we know there's friction acting in this direction. There is 30m sine theta acting in this direction. So what about acceleration? We can use resultant force equals mass into acceleration to find the acceleration for this part of the journey. what would that be? Is there any forward force? There's no forward force. Backward force is friction and 30m into sine of 30. Angle is still 30 here. Yeah. That equals mass of particle A, that is 3m, into acceleration. You can find acceleration of the particle using this. Now we already know that friction is equal to mu r, and we calculated that earlier. Mu r is the same as before, right? 515 under root 3. Mu r becomes this. 15 under root 3 into m into mu. 15 under root 3m times mu minus 30 sine 30 is 15 times m, that equals 3m times a. A is appearing in every single term, that gets cancelled, and we're left with minus 15 under root 3 times mu. Minus 15 equals 3 times acceleration. In fact, we already know the value of mu. We found that in the previous part. Mu is under root 3 over 10. We can also input that here. Let's input the value of mu here as well. That was under root 3 over 10. And that is going to give you the value for acceleration. Minus 15 into 3 divided by 10, minus 15 divided by 3. Acceleration is turning out to be minus 6.5 for me. From y to z, this is the acceleration that I'm getting, minus 6.5. Now what we can do is we can say this is the acceleration for y to z part of the journey. Let's use that here. Acceleration is minus 6.5. And now what are we looking for? We're looking for time. Which equation connects these four things? V equals u plus at, and that is what is going to give us the value of time. 0 equals 0.4 minus 6.5 times t, and the value of t turns out to be 0.4 over 6.5, which is 0.06154, or you can say 0.0615. And that's the value of t that we get here. That's our final answer. That's the time taken to go from y to z here. Make sense? That's the last part. And that completes this paper. I hope that makes sense. That's it for today. Then if you have any quick questions, you can let me know. We will not have our mechanics class on Wednesday. It will most likely be on Saturday instead. All right, instead of Wednesday, it will be Saturday. Because on Thursday, we have a P1 exam. So most of the people will be busy with that on Monday, on Wednesday, in fact. So we will only have a long P1 session on Wednesday, no P3, no M1, sorry. Tomorrow is going to be P1 and S1. And the next M1 class is going to be on Friday and Sunday. Yeah, so library will be P3 and M1 on Saturday then. Sunday is going to be very difficult. The other possibility is I could probably do, no, that will be too many sessions for one day then. I was thinking of Thursday, but that will be 2 M1 classes. Sorry, Friday, but that will be two M1 classes then. Sunday will not be possible, unfortunately. Sunday is, yeah, Sunday is quite busy for me at home. So that will not be possible. Okay, all right, that's it for today. Thank you for pointing out the careless errors promptly as well. Otherwise, it ends up wasting time at the end trying to figure them out. That's it for today. I'll see you again in the next session. Allah Hafiz.